Every single time you update your phone, get an email that's actually from your bank, or use a secure app, there's this invisible cryptographic dance happening in the background. It's all powered by digital signatures. They're kind of the unsung heroes keeping our digital world trustworthy. So let's pull back the curtain and see exactly how they work step by step.
All right, here's our game plan. First, we're going to tackle the big problem. What even is digital trust? Then, we'll get our hands on the tools of the trade, a pair of what I like to call magic keys. From there, we'll follow our sender, Alice, as she cooks up a signature. Then we'll jump into the shoes of our receiver, Bob, and see how he verifies it. And finally, we'll wrap it all up by looking at what this process guarantees and where it can all go wrong.
Okay, let's make this real. You get an email. It says it's from your bank. The logo looks right, the language seems legit, it's asking you to confirm some details. But how do you really know? How can you be 100% sure it isn't some super clever scam artist on the other end? Well, that question right there is the entire reason digital signatures exist.
To solve that problem, any good digital signature has to deliver on three huge promises. Think of them as the three pillars of digital trust. First, authentication. Is the person sending this who they say they are? Second, integrity. Has this message been messed with in any way since it was sent? And third, non-repudiation. Can the sender turn around later and deny they ever sent it? These three things, they're the whole point.
So before we can sign anything, we need the right tools. And the entire system is built on this really brilliant idea in cryptography. It all starts with creating a very special, mathematically linked pair of keys.
Let's go back to our sender, Alice. She runs a special algorithm and generates two keys. The first one, her private key, is her deepest, darkest secret. Think of it like a one-of-a-kind personal signet ring. She guards it with her life. The other key, her public key, is basically the opposite. It's like a perfect mold of her ring's impression. She can give copies of this key to absolutely everyone, post it on the internet, shout it from the rooftops, because anyone, like our receiver Bob, will need it to check if her seal is genuine.
Okay, Alice has her keys, she's all set. Now she wants to send a secure message to Bob. Let's walk through exactly what she does to create that digital signature.
It's a pretty elegant two-step process on her end. First, she's got to create a totally unique summary of her message. Think of it like a digital fingerprint. Then, she takes out her secret signet ring, that private key, and uses it to lock that fingerprint up tight.
So let's zoom in on that first step. Trying to sign a massive document would be incredibly slow. So instead, Alice takes her message and runs it through something called a hash function. This thing is like a cryptographic blender. It doesn't matter if you put in a single word or the entire text of a novel. It spits out a short, unique, fixed-size string of characters. That's the hash. It's the message's unique fingerprint. And what's wild is, if you change even one comma in the original message, the hash it produces will be completely different.
And now, this is where the real magic happens. Alice takes that unique hash, that digital fingerprint, and she encrypts it using her secret private key. The result of that encryption is the digital signature. It's a scrambled-up version of the fingerprint that, in theory, only she could have possibly created. This signature then gets bundled up with the original message and sent on its way to Bob. And this quote on the slide is the absolute heart of the matter. That single act of encrypting the hash with her private key is what proves it came from her. Because she's the only person on the planet with that key, she's the only one who could have made that very specific signature. This is the bedrock of authentication.
Okay, the message has been sent, it's landed in Bob's inbox. Now the ball is in his court. It's time for him to put on his detective hat and use only the information that's publicly available to figure out if this thing is legit.
So Bob gets two things from Alice, the original message itself and her digital signature. The very first thing he does is he actually ignores the signature for a second. He takes the message he got and he runs it through the exact same hash function Alice used. This gives him his own version of the message's fingerprint. Let's call that H1. This is his clean, independent point of reference.
All right, next, Bob takes the digital signature that came with the message. He finds Alice's public key. Remember, she shares that with everyone, and he uses it to try and decrypt the signature. Since the public key is the mathematical partner to the private key, it should unlock it perfectly. And when it does, it reveals the original hash that Alice created way back at the beginning. We'll call this one H2.
And this is it. This is the climax of our whole story. Bob is now holding 2 digital fingerprints. He's got H1, the one he just calculated himself from the message he received, and he's got H2, the one he just unlocked from Alice's signature. The entire security of this whole setup boils down to what happens next. Bob compares the two. He puts H1 and H2 side by side. And here's the moment of truth. If they are absolutely identical, the signature is valid. And that one match proves everything at once. It proves it came from Alice because only her public key could unlock it. And it proves the message wasn't changed because the fingerprints match. But if they're even a single character off, bam, invalid. Something's very wrong.
So you can see how powerful a valid signature is. Let's just take a moment to circle back and be really clear about what guarantees this gives us, and just as important, what can break this chain of trust.
When Bob gets that valid stamp, we've hit all 3 of our goals. Authentication, check. Her public key worked. Integrity, check. The hashes match so we know nothing was changed. And non-repudiation, big check. Because only Alice has her private key, she can't ever convincingly deny that she was the one who signed it. It's locked in.
Let's just run through a quick real-world example to lock this in. Alice wants to send an instruction, transfer $1,000 to Bob. She hashes that message, then signs the hash with her private key. Bob gets the message and the signature. He hashes the message himself, then decrypts her signature with her public key. The 2 hashes are identical. He knows for sure that the request really is from Alice and that a fraudster didn't change it to say, transfer $10,000 to Mallory. So if you boil this entire process down to its essence, it's really just these 2 simple formulas. Signing is, take a hash of the message, then encrypt it with your private key. And verification is, take a hash of the message yourself, decrypt the signature with a public key, and see if the 2 hashes match. That's it. Simple, beautiful, and incredibly powerful.
But, and this is a really big but, this whole system is only as strong as its weakest link. The number 1 risk is private key security. If a hacker steals Alice's private key, they can sign anything they want, and it will look perfectly legitimate. On top of that, the algorithms we use have to be strong enough to resist being cracked, and the software itself has to be written perfectly. Even a tiny bug in the code can open up a massive security hole. The entire chain of trust has to be solid from end to end. And that really leads us to the most important takeaway here. The security guarantees of a digital signature are only as strong as the system that supports them. The underlying math is rock solid, but it's the real-world stuff, how we protect our keys, how we write our code, that determines whether we can actually trust the result. And there you have it, the anatomy of a digital signature. It's this beautiful, intricate process of public and private keys that creates a verifiable seal of trust in our digital world. So the next time you see that little padlock icon or a verified checkmark, you'll know about the amazing cryptographic dance happening just beneath the surface. Now that you're in on the secret, where do you think you'll spot it next?